In this lesson, we're going to look at some more theorems that deal with chords and circles. So the first thing, too, when you're looking at these problems is you have to decide, are you dealing with a situation where you're trying to find a segment length, which is going to be new in this video, versus an angle measure formed by two chords, which we saw already. So the first theorem here is dealing with the segment lengths of chords. So if I look at this formula or this description here, what it's really saying is the product of two parts of a chord is equal to the product of the intersecting chords parts. So AB, so A times B, so these two parts of the chord being multiplied together is equal to the product of the other parts being multiplied together. So you might think of this as part 1 times part 2 is equal to part 3 times part 4, meaning you're just multiplying. So if this was part 1, part 2, part 3, and part 4, you're just multiplying the parts together. I sometimes shorten this and they'll say PP equals PP just because it sounds weird, so it's easy to remember. But really remembering that all of these numbers would be different. So they're not all the same number, so this representation is not the best representation, but it's an easy way to remember it. So if you look at this first example here, we have a circle with two chords is marked. So when I see this, we're trying to find the length of x. So I'm going to use that part times part equals part times part. So I'm going to just multiply the two parts together. So these two are going to get multiplied. So 12 times x. And the way that you multiply does not really matter because it's commutative. And then 8 times x plus 2. Make sure the x plus 2 does go in parentheses though, since it's a binomial. So distribute that 8, so we have 8x plus 16. Subtract the 8x, so we have 4x equals 16. Divided by 4, we get x equals 4. So that's it. So it's a basic problem, but you have to know the theorem or the formula to use to set it up. So looking at the next theorem here, there's lots of different ways to write this, but basically what it's saying is if you have a radius, or I could extend this and say a diameter, so just keep that in mind. So if you have a radius and a diameter that are perpendicular to a chord, what it's doing is it's bisecting that chord. So it's creating two congruent pieces. So if you have a radius perpendicular to a chord, you're bisecting the chord. If you have a radius that's bisecting the chord, so if I see the two congruent parts, well, then I know that this has to be perpendicular. So basically the converse of this statement, going the opposite direction. And then if you have a perpendicular bisector of a chord, well, then that must mean that it has to be a radius or it has to be a diameter. So if I see these two segments that are intersecting, and this segment OD is a perpendicular bisector of AB, meaning it's going through the midpoint and it's perpendicular, that means that point O must be the center, or OD must be a radius, and this entire thing must be a diameter. So using this idea, let's look at this next problem here. So right away I see a diameter perpendicular to a chord. So that means the chord bisects the radius. I'm going to say that the radius bisects the chord. So that means when I look at this, or I should say the diameter is bisecting the chord. So if we have that the diameter or the radius is perpendicular to this chord, these two parts here have to be equal. Another thing to pay attention to for these problems is to look for your radii. So I have a radii here, or radius here. I have a radius right here. So that means this entire length, so if this is 5, this entire length here would have to be 5, which means that this section here that I don't know would be 3. So then when you're looking at this, I'm just going to get rid of this 5 so it's not confusing looking. But when I look at this, I see the situation that I have a part times a part equals a part times a part. So meaning I have this whole thing here times 2 is equal to this part times this part. So I end up having this whole thing, which is 8. So I'm going to go ahead and use that PP times P. So PP equals PP. So I have x times x equals 2 times 8. That's one way to set this up, because this is where they're intersecting those two chords. Remember, a diameter is a chord, so that still applies to this formula. So I have x squared equals 16. So square root both sides, we get x equals 4. Well, it's really x equals plus or minus 4, but I'm only going to keep the positive because it's a length. So that's one way to do this problem. Another way to look at this would be to go ahead and sketch in this other radius. So there's another radius right here. So if this is x and this is 3, and I know that this is a right triangle, I could use the fact that this radius is 5, since all radii are equal, and then you end up with this situation that you have a right triangle, and you could use Pythagorean Theorem to solve this. So that is another option, and you'd end up getting x equals 4. So same answer, different way of doing it. But again, being able to look at this picture and find radii, or even in this one, having to sketch in that radius, very important for solving this problem. So let's go ahead and look at the next theorem. So the next theorem says that if you have congruent chords, then they must be equidistant from the center. So as long as you know that the chords are congruent, they're going to be equidistant from the center. And if you know that the chords are equidistant from the center, then they are congruent. So meaning both ways works for this. One thing I do want to mention though, so if these two chords are congruent, notice this distance right here is congruent. It has to be the perpendicular distance. So when we measure distance from a point to a line, we're always measuring that perpendicular distance. So when we talk about the congruent distance or the equidistant part, it's always the part that's perpendicular, or the segment that's perpendicular to that chord. So if we look at this example here, CD is 16. So this entire thing is 16. This entire thing is 16, AB. So right away, I'm seeing two congruent chords. So these two chords are congruent. So that means if I have congruent chords, these must be equidistant from the center. So congruent chords are equidistant from center. So what that tells me is that OE is congruent to OF, because those distances right there are the perpendicular distances from the center to those congruent chords. So those are the distances that are congruent. So this really tells me that OE is congruent to OF. So then what else we're given here is that OB is 10. So as soon as I look at 10, red flag going off saying, okay, well, that's a radius. So that also means we have some other 10s here. We know that OE is not a radius because E is not on the circle, but this entire thing here would be 10. That is 10, not 16. That is a radius, so that's important. And then it says we have marked perpendiculars, which we can see in the picture. But right away, when I'm seeing this marked perpendiculars, they're really trying to point that out to us. And also, when you look at this picture, you should see if you have a radius or a diameter that's perpendicular to a chord, we know that these two parts here have to be congruent from that theorem above that says a chord or a radius perpendicular to a chord means that the chord bisects. Let me start over. If the radius is perpendicular to the chord, then the radius is bisecting the chord. So that can be used so that we know that basically these parts here are 8 and 8 because half of 16 is 8. So I am trying to find the length of OF. So the quickest way that I'm seeing to do this is because I know that OF and OE are congruent. I see this right triangle right here. I'm thinking let's use Pythagorean Theorem. I'm thinking that's the quickest way. So I'm going to just make a note here. The other conclusion that I made was the fact that I had a radius perpendicular to the chord implied that the radius bisects the chord. That's how I got this 8. And now what I'm going to use is Pythagorean Theorem. So I'm going to go ahead and put an X here, and I'm going to use Pythagorean Theorem since I have the right triangle. So x squared plus 64 plus 100. So x squared equals 36. Square root both sides, and you end up with x equals 6. So that means that x is 6, which also means that OF must be equal to 6, since those two segments represent that equidistance from the center. So that's the way that I thought to do that. You could have just said, if you remember your special right triangle 6, 8, 10, you could have just gotten it that way. You could also use the part times part equals part times part in this for this one. Because I have BF, I could have called OFX, and then this little section here would have been 10 minus X. So I could have done 10 plus X times 10 minus X equals 8 times 8, and you would get the exact same answer. So it's another way to do it. It's just whatever way you see first, and whatever way you feel is the easiest way to do it is the way that you would approach this. So let's go to the next page here. One last theorem to look at. This one's a lot shorter. So in this one, in a circle, parallel lines intersect congruent arcs. So what this means, so if you wanted to shorten this, you could say in a circle, if you have parallel chords, really, for the circle, you're not going to really have lines. You could have lines, but parallel chords implies congruent arcs would be the way that you could shorten this. So if you know that these two chords are parallel, that means that the arcs that those are cutting into have to be congruent. It does not mean that the arcs above and below those parallel lines are congruent. It's just the ones that are between the parallel lines, so the ones that they're cutting into. So if you look at this example here, these two segments or chords are parallel, which means these two arcs right here have to be congruent. You're given a central angle, so if the central angle is 40, that means that this arc has to be 40, which also means that this arc over here has to be 40. So instead of writing that all up just for time's sake, I'm just talking through it, but if this, I would want you to be writing this and explaining it if this was something you were turning in. So I have the parallel chords, which gives me the congruent arcs. The central angle is equal to the arc. And then the last thing is all of the arcs have to add up to 360. So if I just subtract off what I have, so I have 360 minus 40 minus 40 minus 160 gives me 120. So that's what x is going to be. So x equals 120. That's what's left over. So that's it. So lots of different theorems to think about here. So get your key ideas written down and check your understanding problems, and we will talk about these in class tomorrow.